Hey everybody, this is a modified version of one that came out in 1984 here. It says two satellites, right here and right here, of masses m and 3m respectively are in the same circular orbit about the Earth's center as shown in the diagram above. The Earth has a mass of m sub e and radius of r sub e. In this orbit, which has a radius of 2re, the satellites initially move at the same orbital speed v0, but in opposite directions. So first thing they want to know here is calculate the orbital speed v sub 0 of the satellite with mass m in terms of g, me, and re. So let's start to write this down. So first step, as we do in all of these centripetal motion problems, is we say the sum of the forces is equal to the mass, and this is just a generic mass of something going in a circle, times centripetal acceleration. So F equals ma, but the a is the centripetal acceleration because we're going in a circle there. Now here's where we normally add up all of our forces. Well, there's only one force on these satellites here, and it's just the force of gravity from the Earth. So we'll write the force of gravity is equal to, and we'll substitute in for centripetal acceleration, so that becomes v squared over r. Now let's plug in for the force of gravity here. So you don't do m times little g. This is the true force of gravity from the universal gravitational law. And so we'll do big G times the mass of the Earth is 1 times the mass of the satellite. And again, I'm keeping it a generic m right now, over top of r squared. So all of that is Newton's universal law of gravity. On the other side, we have m v squared over r. So we'll see a few things happen here. One is that the mass of the satellite cancels out on each side of the equation, and that the radius here cancels out with one of the radii there. And so now we basically, all we have left is v squared on this side. So we just need to take a square root basically of whatever is left over here. So v then is equal to the square root of big G times the mass of the Earth over the radius. Now, so far I've been keeping this radius generic, but this radius should be the radius plugged in from the problem. So on the problem here, they are at 2r sub e. So let's plug that in there, 2r sub e. And so that is our answer for the orbit of the satellite of mass m there. So next part here, and I'm just going to keep this here for a second because I'm going to go right back to it. It says, how does the mass of the 3m satellite affect its orbital speed compared to the mass of the m satellite? Justify your answer. So let's look right here. Well, the mass canceled out. So it wouldn't matter if I called it m or 3m or whatever, the masses cancel out. So the way to answer this is no difference. And then when you justify your answer, you want to say something like, the masses cancel out of the equation. All right, so finally, part C here. They say, what is the period of rotation for the 3M satellite? Well, one thing to remember is we just said the velocity is the same for either one. So we still know the velocity for this 3M satellite. It's what we just solved for. So the velocity is equal to the square root of capital G times the mass of the Earth over 2re is our radius there. So not only is this the velocity, but they want the period. So then we got to think about another part of velocity, and we often forget this when we're doing these equations, that velocity is also the circumference over the period, or 2 pi r over the period. And by the way, this r here I'm just keeping actually generic. That's a generic r, so I'm going to have to fix that in just a second. Well, let's go ahead and do it. Let's write it as it's normally the radius, but in this particular case, the radius is 2re. And so we'll put that over top of t there. So v is equal to this and v is equal to that. They asked for the period, so all we have to do is some rearranging here with some algebra. So I'll multiply the t up to the other side so that I get the period is equal to. Out here on the outside, I'm going to get 2 times 2 is 4 pi times re. And then I'm going to divide by all of this, so I can just flip it underneath the radical. And so this is 2re over top of g times the mass of the Earth. Now you can just leave it like that if you want. You can clean this up a little bit. Like, it's, for some people it's weird to have an RE outside of the square root and RE inside, whatever. Doesn't really matter there. If you brought this inside, it'd be r squared, and times that would be r cubed. So if you really want to write that, you could say the period is equal to 4 pi times the square root of 2 RE cubed over GME, like that.